Okay, so welcome everybody. My name is Giovanni Pizzi. I'm from EPFL Switzerland. And today, together with Taylor Baird, Doudou, and Sarah Bonella, we'll be presenting OSSCAR, which is a collaborative platform for open software services and classroom for research. The program of today will include 4 short talks. I will first start introducing what OSSCAR is, what are the goals, the activities we are having in this project. Then we'll have Taylor present an example of a prototypical notebook we've been developing with OSSCAR, followed by a technical presentation going a bit more in detail about how to actually generate the content by Doudou. And finally, Sarah will give a kind of wrap up and a call for action if you're interested to contribute to what we're doing. And at the end, we'll have a Q&A session. So we ask you, if you have questions, to type them in. At the bottom, you should have a Q&A button with 2 bubbles. You can just at any time already, even during the presentation, press on the button and type in your questions. At the end, we will read through them and try to answer all of them. The other final comment is that this webinar is being recorded, and all the material, the video, and the slides will be shared on the website of SICAM. So you will find everything online also after the webinar is over. So let me start with a brief mention of what OSSCAR is and what is its goal. So OSSCAR is a project which is being funded by the EPFL Open Science Fund. The project started back in 2019, is running for 3 years, and is going to finish at the end of this year. The goal is to create a collaborative environment to develop visualizations which are interactive and are mainly tailored and targeted for education and teaching using an open science approach. And this feedback loop kind of explains a bit our idea, where the content and material we prepare for OSSCAR, on one side, is a way to help teachers prepare and use more material. It also helps directly the students to have a more effective learning with a more hands-on approach. And also, the content is actually shared between research and teaching. We'll see some of the content we present actually originates from research questions, and vice versa. Some of the material we're preparing can be used directly for research. And what OSSCAR tries to do is really foster this positive feedback loop where all these different actors can then go and contribute back, improve the material, and in this way encourage further material to be generated. In OSSCAR, we target 2 main use cases, which is having live demos during classes, as well as self-learning. And we see in the next presentation by Taylor a demo of one prototypical example. Here you see 2 little animations of 2 applications we've been developing, one for quantum mechanics on the left, and one more targeted to atomistic simulations with the construction of norm-conserving pseudopotentials. But the idea is that we try to address both needs at the same time. The content is actually created mostly by us at this stage, but we encourage, actually, the goal of this webinar is also to encourage you to be involved if you're interested, and originates now from 2 classes that we've been teaching at the EPFL. But as we'll see, we try to address very common problems and with a very common technology, which can be used across many different disciplines. The goal of these live demos and this self-learning is really to have the students be allowed to do live exploration and understanding in a deeper way of different phenomena by directly playing both with the visualization and with the different parameters which constitute the model of the simulation. The same technology can be used for many other purposes. I just mentioned another one, which is not the main goal of OSSCAR, but for which some of the components we've been developing and using can be used, which is live grading, where you have a notebook, an interactive notebook, where you can have students ask questions to students that they can answer. I can even grade them. But that's not the current goal of OSSCAR, and what we see mostly addresses the 2 main use cases I mentioned at the top. So what does OSSCAR actually do? And here I try to list 4 main action types we do, and we describe them one by one in the next few minutes in independent slides. The first one is we are, by design, an open science project. And so we try to use as much as possible open science technology and the existing well-established software like Jupyter, Voila, etc., with the idea that we want the content we create to be there and be easy to use by many people without having to learn a specific technology, and also to be there and working for a long time. Still, there might be missing components, missing visualizations, which are more specific to the domain, our course material. And so we contribute with the development of custom components, technological components. The second thing, as I mentioned, we developed educational content. We actually developed actual interactive visualizations and notebooks for the courses which are typically addressing currently computational chemistry, computational material science, and computational physics. And the third important thing we do in OSSCAR is to help and facilitate teachers, other teachers, to create new content. And we do this in a number of ways by having documentation, how to use technology, examples, and implementing, as I said at the beginning, new widgets to visualize specific content, which is typical for our courses. And in all of this, we try to, from an educational point of view, to encourage computational thinking in students, help them learn better. But also at the same time, we try to make it in a fully open way. So we also encourage students who are interested to actually go into the code which composes these visualizations, play with it, learn better, and also contribute back with improvements and further extensions, which can be useful also for the next generation of students. I will go, as I said, I will go now through very briefly these few points. The first one is we try to use well-established software. Our choice has been to use Python and work in a Jupyter and JupyterLab environment. The reason is that Python is a very common and widespread language, programming language in our community. It's quite easy to use and to code. And there are many good libraries available, starting from 2D and 3D plotting, but going to data processing, data analysis, machine learning, and what more. So it's very easy to write very few lines of code, relatively advanced algorithms. At the same time, combining Python with Jupyter and JupyterLab allows to create simple graphical user interfaces to make all this visualization interactive, just knowing Python without having to learn other languages such as JavaScript, for example. And finally, since we want to make it also easy to give access to these notebooks to students without having to learn and install dependencies, etc., we also leverage the fact that tools exist to convert these notebooks into simple web applications, as you will see in a moment. And finally, all what we do, we share on GitHub. We'll see all the links later in the slides, with the goal of really encouraging an open science approach in a global sense, not only to use the code as an example, but also to reuse the educational content for other classes. For what concerns the custom content we create, as I said, even if you use standard technology, there might be specific visualizations which are typical for what we do, like visualizing the first Boolean zone of a crystal and a typical path for a band structure, or custom visualizer for which are tailored to show band structures, electronic band structures, projected density of states, etc., which we actually developed inside OSSCAR to use them in our notebooks, but actually are very generic and are very easy to use. So in very few lines, you can actually use it in your notebooks for your, even for your research, not only for teaching. Here I'm showing two examples. You will see some more examples later in the next presentation by Taylor and Dole. And then, as I said, our goal is not only to produce new content, but it's actually also to make it easy for other teachers to leverage what we learned, leverage the technology we are actually developing in addition, and to make it easy to have new content. For this, we have a documentation how to develop new content. This is on our website, oscar.org. And all the material we produce is actually, as I said, fully open source. And this actually, besides reusing of the content, also serves as a library of code examples. So you can actually start from an existing visualization, adapt it for your needs, and use it for a different course content application. And one important thing we also do, and you will see later in the Dole's presentation, what are the solutions we suggest, is also thinking and suggesting what are solutions for deployment of these apps. So deployment means how you make these notebooks easily available to students. If you just have a notebook, and even if you put it on GitHub, still a student has to know how to install JupyterLab, install the dependencies, run it. What we want is really to have a zero setup approach for students where they just open a browser, they click on a link, and in a matter of a couple of seconds, they can immediately get to one of these visualizations and start using them to learn. And this is very important, especially for our use case, which is for live demos during a classroom where you don't want the teacher to wait 3 minutes before they can start a visualization to show a specific concept to students, or also for self-learning where our notebooks are designed to be very short and self-contained, focusing one single application. And so you want students to be able to quickly switch between different notebooks without having to wait too long. And what we've been doing is to identify different solutions, different ranges of solutions, which all have pros and cons. Like there could be solutions which are fully open, but maybe it's slower to load, or solutions which are fully free and faster, but maybe require an institutional account. And this is what we also describe and discuss in the documentation of OSSCAR to make it easy for other teachers to achieve the same goal. With this, this finishes my introduction of what OSSCAR is. So I will now give the word to Taylor, who will show you a demo of a typical application so you can get a better sense of what we are actually doing now. Please, Taylor.
Thanks, Giovanni. So,
perfect. Yes, you can go ahead.
My name's Taylor Baird, and in the next 15 minutes or so, I'll show you an example of how an interactive lesson using a notebook from the OSSCAR project may look like. In the example I'm about to show you, well, the demonstration will follow the particular format that's been employed in a typical OSSCAR notebook. However, you should bear in mind that this format is entirely flexible and can be tailored to your preferences. I won't be giving you any technical details right now on how to create such a notebook. Rather, Dush will show you how to do this shortly. If you'd like to check out the notebook yourself, the link is given at the bottom of the slide, and all materials will also be shared at the end of the webinar. So, for the purposes of this demonstration, I'll here consider a notebook that demonstrates the split operator Fourier transform, or SOFT method, which is employed in quantum molecular dynamics simulations to solve numerically the time-dependent Schrödinger equation. The notebook is fully rendered here as a web page using a tool that Do shall show you shortly. At the top of every one of these notebooks, we have a list of authors, which shows who has each contributed to work in developing the notebooks. We believe this is a nice way to simultaneously acknowledge and encourage work on new notebooks. The goals of the notebook are clearly pointed at the top of the notebook itself. This serves to immediately orientate the students with regards to what they're expected to take away from the lesson, and the teacher can give some brief elaboration on these in order to help the students focus on the main core concepts of the notebook. We found that any supplementary background information used to review background theory, for instance, be stored out with the main notebook. And this can be linked in the background theory section here. Next, we have a section of tasks and exercises which are posed to the students, guiding them in their usage of the notebook. These tasks play a crucial role in focusing the students' efforts in fulfilling the learning objectives and making sure they address the core concepts the teacher wants to have conveyed. The tasks include some instruction on how the subsequent parts of the interactive notebook should be used. The remainder of the lesson shall consist of the teacher working in tandem with the students to interact with the various components of the notebook to solve these aforementioned tasks and fulfill the learning objectives from the start. Just before the actual visualization pane itself, we have two sections here which include a series of widgets which allow the user to control the parameters of the simulation. Here we have a set of sliders, drop-down menus, and checkboxes further down. It seems natural to first play around with the interactive section of the notebook, describing for students what exactly they're seeing in these simulations. So, to that end, an instructor could simply choose the default system, here a box potential, along with the default simulation parameters, the time step and mass of the nucleus that we're considering in the simulation, and set the simulation running. Now, with the simulation running in the background, they can take the opportunity to expand on the visualization. So what we're seeing is, starting with an initial Gaussian wave packet and having chosen a box potential, the soft method is utilized to propagate the wave packet in time according to the time-dependent Schrodinger equation. The interactive figure consists of 4 subplots. In this top left subplot, we have the evolution of the wave packet and the position representation. The chosen potential is superimposed on this subplot. One may also use radio buttons below the visualization pane to choose which components of the wave function would like to view, the real, imaginary, or modulus of the real, imaginary parts or modulus of the wave function. The top right subplot shows the evolution of the wave function and the momentum or P representation. And in the bottom left, we can view the evolution of the different contributions to the total energy of the system. In black, we have the graph corresponding to the total energy, in red, the kinetic contribution, and blue, potential. The bottom right subplot shows us the evolution of the total norm of the nuclear wave packet. Next, we demonstrate how, by interacting with the various widgets included in the notebook, we can investigate a large range of different parameters and systems and rerun the simulation with a click of the button. This method of teaching is demonstrably more flexible than conventional approaches, which typically rely on static images, or if any images at all. Let's now use the interactivity of the notebook to answer the questions in the tasks and exercises section and address the goals outlined at the start. As examples of the flexibility available to us, we can use this, again, the default box potential, and use the default simulation parameters to see how the soft method indeed captures various quantum effects, such as the effect of quantum tunneling, which will have been encountered in previous classes. With the default height and width of the potential, we can see that when the wave packet collides with the box, we have a complete absence of tunneling. There's simply a reflection of the wave packet back into the left-hand part of the simulation box. However, when manipulating the various sliders which control the parameterization of the wave packet, of the potential, sorry, we can see that it's possible to manufacture a regime in which we now have the possibility of finding our particle on the right-hand side of that box potential. We have complete tunneling through the box, even for an energy which the system would be classically unable to do so. We can also see the Heisenberg uncertainty principle manifest itself by looking at the wave function evolution and the position and momentum representations. Or we can quickly switch, again, very simply, to this Morse potential and investigate the role anharmonicity plays in the evolution of our wave packet by playing with the different parameters which parameterize the Morse potential. This immediate response of the visualization to inputs from the students allows them to test their intuition and current understanding of a concept. Let us now observe the evolution of the various control quantities, the contributions to the energy of the system, in order to answer the question which pertains to the stability of the algorithm. So, using the default time step and mass, which is set so that the time step is sufficiently small to render the algorithm stable, we see that the total energy in the black curve in the bottom left plot remains essentially constant. We have precise energy conservation for this time step. However, If we go back and increase dt, the time step of the simulation, and rerun, we can see that for a sufficiently large time step, this energy conservation is broken. And this black curve behaves completely erratically now. Again, this seamless, essentially instantaneous visual feedback allows us to achieve an effective means of conveying an important aspect of the method and its dependence on core input parameters. Key messages to be taken away from this demonstration. The teacher can also prompt the students to have think about the underlying reason for this breakdown in energy conservation and point them to this background theory notebook if they perhaps require a refresher. Finally, the notebook is written so that students may also use it after class without instructor supervision. There's a supplied legend at the very bottom of the notebook, which is comprehensive and guides students in their usage of the different visualization parts of the notebook, along with in-depth solutions to the various questions that are posed to them. These solutions are hidden by default, which encourages students to attempt to answer the questions themselves. This in turn promotes an active approach to learning, which has been shown to improve the effectiveness of a lesson. Okay. So here I've shown to you the typical structure of an OSSCAR notebook. Thus far, we have a modest collection of such pedagogical notebooks. Our ambition is to, with the help of contributions from the community, construct a growing library of the notebooks, which shall be useful both individually and in combination. Thank you for your attention, and I'll now pass you on to Boo.
Hello, my name is Dodu. So today I will just talk about how to make this interactive application for Jupyter notebooks. Basically, there are 3 steps to create a notebook and offer it to the student. The first step is to prepare the Jupyter notebook. And for the interaction, the main component is the Jupyter widget. Second, we need to convert the Jupyter notebook into web application. We use a program called Voila. After we have the web app, we need to distribute to students and teachers. There are 3 ways. I will show you 3 ways where you can deploy your web applications. So for in the Jupyter, the interaction is played by the Jupyter widget. It's a main component for the interaction, and there's a package, Python package called EPIL widget, which provides many basic web widgets like buttons, sliders, and the widgets are showing as a front end components. So that's what you can see, and also the widgets are connected to the Jupyter kernel on the back end. That means the appearance can be dynamically updated from the Python code, and also value can be also read from Python. This is very essential for the interaction. So here is an example. We initiate a float slider, which the range is from 0 to 10, and the default value is 7.5. So once you have the widget, you can move the slider, and the value has changed. So you can just read the value. So it's 8 now, and you can also set the value. So here it's go back to 3. There are many standard widgets for general purpose usage offered by EPIL widget, like drop-down radio buttons, text area, and passwords. If you want to know more and how to use them, please go to the EPIL widget homepage. There you can find more information. In our notebook, we use matplotlib for a lot, for like 2-dimensional interactive figures. So matplotlib is a comprehensive Python library for visualization. And we can also use matplotlib figure as a Jupyter widget by putting this %matplotlib widget at the top of code. So here we give an example. For example, if we want to teach a student how the same function, we plot the same kx function with matplotlib, and then we want to use a slider to control the value of k. So after that, we need to connect these two widgets. That's we use this observe methods from the widget slider widget and define a callback function. This means when you move the slider, when the position has been updated, it will trigger the callback function on slider change. Inside the function, the data has been recalculated, and then the line of the has been replotted. So here, when you just move the slider, the figure has changed instantly. So this makes the figure interactive. Under our OSSCAR project, we develop some also custom widget, like particularly for computational material science. For example, here we develop in the interactive periodic table widget. So we have a periodic table. People can use mouse, click the element, and the color can be changed. That means we allow the element into some different states. For example, must be present or must be absent. And you can also define the color, and you can also disable elements. So that's means when you click the element, nothing will happen. So here example how we use this periodic table. So inside the open database integration for materials design, which is also called Optimate, we use this interactive periodic table as an element filter. So once you click one element, the color will change to green. That means this element must be included. If you double click the element, the color will change to red. That means this element must be excluded. And you click again, it will back to normal blue color. After we have the interactive notebook, we need to convert into web applications. There is a program called Voila, which is developed and maintained by the Jupyter development team. This program can convert Jupyter Notebook into a living web application. Why is it called living? Because once you have the web application, it will first run the Jupyter Notebook and hit all the input code and only show the output cell like text, widget, figure, and also markdown. But still, when you click the button, it still connect to the Jupyter server. So that's means when you click a button, it will trigger callback function on the back end. After running the code or simulation, it will give feedback to the front end, to the web page. So after we have these web applications, we need to distribute to people if we want to teach students or share with other people. So that's why we need deployment. I mean, there are many ways to do that. And the first option is a free one. It's called mybetter.org. It's a website that offers a free service to open live Jupyter Notebook. And it's working smoothly in combination with Voila. So basically, there are 3 steps to do that. First, you need to publish your notebook on the Jupyter Hub and do some setting. And you must make sure your GitHub repository is public. Then you open mybetter.org. Inside here, you input the GitHub repository name, branch name, and also notebook file name. In order to use Voila, you should put pre-pending Voila render before the URL. After that, just click button launch. After some times, I mean, maybe first time maybe minutes, you will get the web application And you can share this link to other people. When other people click, they will also get the same web applications. So MyBinder is free, but a bit slow. Open the page may take between 13 seconds or up to minutes. Also, the computing power offered by MyBinder is very limited. So if you want to do some very high, heavy computing or simulation, this may be a problem. So that's why we have the second solution, which is called Duku Server. Duku is the open source platform that for easily deploy web app, and it's also easily integrated with Voila and Jupyter. And thanks for the services offered by Materials Cloud, we set up our own Duku server and we deployed our OSSCAR apps on the Duku server. So as you can see, the loading time is less than 5 seconds in most cases. And you can use your own resources. That means you can have more CPU and more memory, and you can also custom how much memory, how much CPU for each app. However, these methods require advanced system administration. You need to have some experience, and also you need to have experience, know how to deploy the Duku server and app. Note today, many universities and institutions provide this Jupyter Hub for their students and teachers. For example, at the EPFL, we have this Node tool planned for, and the student can use their username and passwords the same as the email, and to log in the Jupyter Hub platform, and they can easily run our interactive notebook. Here you see the example. This our quantum mechanics notebook was running there, and also by this way, is allow the student and teacher can view and also modify the code. They can also distribute and contribute to the code and also the app. This is particularly useful for some advanced teaching, and some course may relate to programming and teaching algorithm, something like that. Finally, I just want to give you some take-home message. As you see, to develop an interactive notebook, the main components is the Jupyter widget. You can use iPad widgets, which offer a lot of common widgets. On the OSSCAR project, we also have the custom widget for material science. And we use Voila, which is very powerful to convert the notebook into web app. Finally, we choose multiple ways to deploy the web apps. There are free solutions like MyBinder, also some advanced one that Duku server. Finally, I would say OSSCAR demonstrate a complete and easy solution to develop and deliver interactive web applications for education. Thank you for your attention. That's all.
Thank you very much, Do. I think now it's my turn to share with you some information. Let me do this by first sharing my screen and then sharing the presentation. Here we go. Hopefully everything is set to go. So my task here today is how to turn what we have done up until now into a much broader community-oriented effort. So how to go from one OSSCAR to many, many realizations of OSSCARs. And in order to share with you our ideas on this matter, I just want to go back to the first slide that Giovanni showed us and remind you that the effort that we have made up until now has been to develop a collaborative environment for interactive visualization for education and teaching. You have seen one example in Taylor's talk, and Do has given you some ideas about the technical solutions that we have identified. Now, the question is, where do we go from here? And this is, in order to answer this question, we're going to need and rely, in fact, on some input from the community in two different aspects. The first one is provide us with feedback. Let us know what you think we're doing right, what you think we could do better. But also, and perhaps even more importantly for the ultimate success of this effort, engage with us if you want, if you're interested, if you see an advantage in the production of new notebooks or in using the notebooks that we have explored and created up until now. Now, in order to do that, and in order to try to share with you as much information as we can on the OSCAR project, the key entry point that you should be aware of is our website, www.oscar.org, which is really, the access point to this project. Now, if you scroll down the homepage of this project, you will find this sort of very simple, hopefully everything is as intuitive as can be on the website, navigation sort of map, right? Which is divided into 4 different parts that we're going to somehow explore together. Now, this is going to be like one of those tours of the European capitals in 3 days, where you see 15 cities in 3 days. So mainly the message that I will try to convey today is go and have a look and take your time to explore the different features of this website. We start from the course applications. You've heard that our main goal is to develop notebooks that then can be deployed in classrooms by teacher assistants, or used by students on their own to improve their learning experience in complex or basic topics in the general area, for the moment, of computational science, but in general, scientific disciplines. This is achieved, as you've heard, by creating a collection of notebooks that are organized in different broad topics. At the moment, we have a rather limited set of topics: quantum mechanics, something quite specific on the band theory of crystals, statistical mechanics, molecular dynamics. You can navigate among these collections simply by clicking on the appropriate box. Now we go a bit deeper in the statistical mechanics one of my favorites. At the moment, we have 3 items. How to experiment and play with a simulation on Ising model, how to build a Monte Carlo simulation to sample the canonical distribution, or how to use Monte Carlo to compute pi. And again, this is like a sort of a telescope type of view, but if you now click on the Monte Carlo simulation, you access the specific item that this box explains, and by simply clicking on one of these 2 buttons here, you have access to the full notebook and interactivity of the notebook as illustrated by Taylor. Now, if we go one step further, the question is, okay, if you think that this is a good idea, if you want to try to use this material for your classes and hopefully contribute with new notebooks to our library, how can you do it? Well, okay, there are 2 steps to it. If you need to get acquainted with the tools that we are using, take a tour in the tutorial for developers that we have prepared for you on the website. And these tutorials are the documentation that Giovanni and Do and Taylor referred to. And as you can see from a very quick glance to the topics here, they sort of take you from the installation of the programming environment, the Jupyter Lab, to the key tools that we use, the widgets. I give you examples of simple ones, the trigonometric function that Do showed you in his presentation, or something a bit more ambitious like the interactive periodic table. And then last but not least, there is this notion that we really want to deliver these notebooks as web applications so that they can be accessed with any web browser. And this is the relevance of the Voila program that we use and that Do has explained to you before. Now, once you have established that, okay, you are familiar with the tools, or maybe you were familiar with the tools even before, there is the issue of how, if you want to, can you add a notebook to our collection? And in order to enable you to do this, we give, in the spirit of open science environment that we want to create, we give you access to the full OSCAR source code through a GitHub repository. So the second most important thing that I would like you to get away from this particular presentation is simply the name and address of our GitHub repository. And if you are an expert enough user, you can simply contribute to this repository, and you can use the repository also to let us know directly about issues or pull requests for new notebooks. If you have questions on any aspect of the project, or in particular on how to contribute, just get in touch. In this navigation map, there is also a part where you can get more information about the general spirit about the project, or you can get information about the team. Now here I only have the pictures of the 2 oldest members of the team, simply because if you click on our names, this will take you to a page where you can find contact details, and including our email address. So you can write directly to us and we can start interacting to see how and if we can collaborate to get your own OSCAR going. Of course, and being the last speaker, it's my pleasure and my task also to say that this project has grown and developed in an environment. The initial funding for the project, which is still running, as Giovanni said at the beginning, has been provided by EPFL through the Open Science Funds. And we are also very grateful to CICAM and Marvel for creating an environment both for dissemination and for development of these projects. Doe has mentioned before that our notebooks are deployed on the EPFL Noto platform. And last but not least, we have used some of these notebooks in classes that we are teaching here at EPFL. So many of our students have played the role of guinea pigs, very active and vocal guinea pigs, I have to say, helping us to improve the format and the content of the notebooks that you will find on the OSCAR website. So as I said, there are only two things that you should really take out of this presentation. And this is an invitation to go and explore our tools, so the webpage, www.oscar.org, and the GitHub, so that you can access all the material and all the information and contribute with new notebooks. That's really all I wanted to say for the moment. So I will stop sharing my screen. Hopefully, yes, go back to a view in which you can see all of the contributors to this project. And I think that's it. Have a wonderful end of the day if you are in Europe, or very good night, given that you are in China at the moment. Thank you.
Thank you, everybody.
Thanks, everyone.
Bye.
Ciao.